All right, guys, let's get started. Thanks for the lively attendance today. So this is our midterm review lecture. So it's just reminders moving forward. Probably not worried too much about the chapter stuff, but the next chapter we have to worry about is way, before lecture E4. So that's like several lectures after the midterm, and I think after spring break. Chapter 4 might be useful to skim through, and chapter 5 might actually have some good nuggets for studying for the midterm, so something to look at on there. Otherwise, assignments, there is still a muddiest point for this week, even though it's just sort of midterm week. So the great thing for you to reflect on is maybe like the easiest, hardest, most interesting aspects of the midterm. Be useful for me to hear that. And then just a reminder that your final project groups, so 3 to 4 names, will be due the Saturday at the end of spring break. So just as sort of timing, we've got this week, then there's next week, and then there's spring break. And so the end of spring break is when I want you to sort of say who you plan on working with in your 3 to 4 person groups for this final project. And then of course, we've got the midterm, which we will talk about today. And I might, let me see if I can show you before I get into the midterm format and everything, just in case you haven't taken a good look yet, I'm going to flip my share here to the Canvas site, which I reorganized a little bit yesterday so that I hopefully made it a little more navigatable. So give me a second to just duo login to Canvas here. And bring up the student view. And then I'll switch my share over. To, let's say here. All right, so let me flip over to computer as well. All right, there, I guess, so everybody sees Canvas. So Canvas, as usual, you go to modules in the student view. Again, you can collapse all at the top. It's a great way because I've got a bunch of modules here, so sometimes it's easier to just hit that collapse all at the top. And then if you scroll all the way down to in between, so we just finished Unit D. So there's this one module here, Unit D/C, Midterm Lockdown Browser Compliance Test. Make sure you complete that ahead of the midterm for sure, but the sooner you complete it, the sooner you get access to the study materials that are inside the midterm unit. So this little module here just has this little compliance test, which is like a 1-question test to just sort of like check this box, and it just makes sure that all the technical difficulties that might come up with running Lockdown Browser are resolved. And then once you complete that, you'll get access to this Unit DE midterm, which right at the very top, it's got this study guides link there, and that's got sort of all of the learning outcomes and study guides from all the previous units. It's got this midterm the review. Those are these slides I'm about to present. Those slides towards the end of them have got some sample problems that might be helpful. And in case we don't get through all of them or you want more explanation, I've got a video that goes through each one of those. And then we've got actually the exams you'll complete. This is the Thursday exam. This is the next Tuesday exam. Those are the ones you'll actually get for points. But then beneath that, I've got a practice problem set that this is, I think, PDF versions here, and then some video explanations for the solutions. And then down here, sample midterms from previous years. So I just threw up some previous years. So the 2020 and the 2019 sample midterms right here. These are a blank version for you to just, you want to just try it without seeing the solutions, and then the solution set there. So there's a bunch of study resources inside that midterm module. So if you haven't looked at that midterm module, definitely take a look at it. It'll give you some good insights into what to expect on Tuesday and Thursday. And then if you haven't completed this lockdown browser compliance test, make sure you do that, or else you won't be able to get into this module, which actually has the real tests in it. So that's where to find everything on Canvas. So let's go. Yes. Uh-huh.
But you said that we could do a Friday, Saturday?
Yes.
It is due.
I will go over that. So I made it, just to put it on your calendar, I made it due on Thursday, but the availability window goes until Saturday. So if you don't want to do it Thursday, you want to do it Friday or Saturday, that's fine. Just know that for stage one, once you start it, you've got 90 minutes and then it's over after that. No, no, it's, I just, generally for most assignments here, even though Canvas marks them late, just because availability dates don't show up on the calendar, I want to give you kind of encouragement to do them by a particular time. So I'm putting like due dates on there, but usually, unless I say specially, if I make an availability window longer, then that's my way of giving you a grace period with no penalty. So you won't be able to turn in the midterm after Saturday night. So you only be able to open it Thursday, Friday, or Saturday. But even though it's due on Thursday, that just means that nominally we're all doing it on Thursday. But if you decide it's more convenient for you to do it on Friday or Saturday, that's totally fine. Canvas will mark it late, but it's not going to affect your score at all. So you can ignore the late marking. And I'll get to that in a second. But that's where to find everything. So any questions about how things are organized on Canvas? Any questions online? I've got things sort of mixed up here. All right, so let me flip back to the other share then. And back to here. Okay, and I'll close this out. All right. All right, so that's what we meant by see Canvas for these things. So just to confirm, the one that opens on Thursday at midnight, Thursday morning, early morning, that's the one you have to do behind Respondus Lockdown Browser. I'll allow you one double-sided sheet of hand-produced notes, basically no photocopying. If you want to type them up, that's fine, but I don't want you to include little screenshots or any sort of copies of material. I want you to produce it somehow. So you can produce it by writing or you can produce it by typing, but it has to be reproduced as opposed to just copied. And then I can also, if you want it, 2 blank sheets of scratch paper. So in the process for doing the Respondus, then I'll ask you to show me your notes and show me the scratch paper, and that'll be that. If you want to do this in this room, that's fine. It doesn't appear like there's ever anybody who needs this room right after ours. So I'm willing to hang out for the whole 90 minutes in this room on Thursday until everyone's timers run out. And that's fine with me. If there is some weird thing where somebody does happen to have this on a one-off on Thursday, we might have to kick everybody out, but I think that's very unlikely. So if you want to do it in this room and have me proctor, that's fine. I will show up in this room. If nobody shows up here within the first 10 minutes, I might leave. But as long as somebody's here within the first 10 minutes, I'll be here for the whole 90, or unless everybody finishes earlier than that. Yeah.
So on stage 1, are all of the questions multiple choice, or are there written answers?
Oh, good question. So yeah, that's kind of the question up here too. I'll get to that, but basically, I mean, it's Canvas based, and so expect the kind of diversity of Canvas questions. I will tell you there are no short answer that are going to require manual grading. They are all automatically graded questions.
Another question. If we get 100% on the first one, do we have to get the second one?
Well, so it's not a replacement sort of thing. So it's 80% of your score is this, 20% of your score is this. So I forget, I'd have to double check the syllabus. Part of the reason I make a syllabus is because I don't remember all my own policies, but let's say that 15% of your grade is the midterm, then you could say, well, actually multiply 15% by 0.8, and that's the percentage that this is. Multiply 15% by 0.2, and that's the percentage that this one is. So it's almost like they're 2 separate tests that collectively are 15% of your score at the end, but it's not like a retake situation where this test is replacing this test or anything like that. But they are identical tests. Yeah.
Do we know right when we take a test what score we got, or do we not know until like the end?
No, yeah, because then that would end up sort of giving you kind of a backdoor to an answer key.
Yeah.
So in between the 2 stages, you don't get solution sets or scores. After stage 2's window goes away, I will manually release solution sets and scores. All right. So any other questions? So I have done in the past retake setups, And students, like, but where I have a different retake, where it's like a different exam. And generally I find that there's very little increase in scores from one test to the other. There's a little bit. And I think I don't actually see a great decrease in anxiety. So far, in all the classes I've done this setup, where I do the stage 2 exam, I actually do see an increase. Like if I were to compare your stage 1 to your collective stage 1, stage 2 score, I do see an increase in scores. I see evidence afterwards for more retention, and students generally so far, I mean, you might hate it, but most of the students I've tried this with so far seem to like this. So have an open mind and tell me what you think of it afterwards. If you hate it, that's really great feedback, and I'll think about doing something else in the future. Yeah.
And then how many people are in the group one?
Well, for the group one, everybody can collaborate. You all can, yeah. So, and you can do it outside of class. You can do it on Discord. You can do it on Slack, however you want. So basically, on stage 2, Monday, the availability window will open up. It says it's due Tuesday, but I'll give you Monday, Tuesday, and Wednesday. It's not timed. So you go onto Canvas and there's no respondus, there's no lockdown, and you can just work on through it. And you can work with somebody as long as they're in this class, enrolled in this class, a current student. You can work with them. You can use notes, your own notes. You can use notes I've provided. You can use Canvas resources. You can use the textbook. I don't want you to go off and use Chegg or any other internet source. But if you've taken notes from this course, or if I've provided it to you or linked it to you, then you can use that resource. And again, it's the exact same exam as stage 1. So at the end of stage 1, I actually have a reminder. Before you hit submit, you might want to use on your scratch paper, write down your answers so you can highlight the ones that were difficult to you. And then you can kind of think about them in between stage 1 and stage 2. And then when you all get together, and you don't have to get together, you can do stage 2 individually, that's fine too. But then when you all get together, you can say, I think I really had trouble with number 4 or number 6 or whatever, and then you can work on those together. So any questions about this weird format? Questions online as well. Okay. All right, so today, this midterm review. Now, basically what follows after this is I've kind of picked out, so I don't have to go through any of the following slides if you guys have questions you'd just like me to handle. But the way this is organized is that we've had 4 sections so far. So basically, I've grabbed the learning outcomes, or you can think of it as a study guide for all 4 sections, and I have that as a title slide. And then I've grabbed, of the lectures from that unit, what I think are kind of the salient points from that unit that I've been hidden behind that. So then I've just sort of repeated those. And then at the end of this, I have some practice problems that I'm happy to work through. If we don't go through, then like I said, there's a video online of me working through those already. Yeah, Eric. Oh, sure, yeah, it says sharing is paused. Thank you. Let me fix that. Where did you go, Zoom sharing guy? Oh, it's up at the top, of course. So those online, apologize for that. Let me pull this back and unpause. That should fix it. Yeah, great. Okay. All right, so before I move forward, and actually as I move forward, if a question comes up, just let me know, and I can stop right there. But before I do that, are there any burning questions, things you want to, oh, the other kind of thing I didn't mention, remember assignment D3, I've extended that deadline, no penalty, until Wednesday night. And I've gone through, and in every submission that has been submitted, I've gone through and found any major errors that I think that Eric might take points off for. I've highlighted and said, you might want to fix this. So every single person who submitted it, I've gone through all of your submissions and highlighted those errors. And so if you haven't get a notification that I left a comment on there, I recommend going and taking a look to see if I left a comment. If I did, I recommend maybe uploading a new submission to make sure you capitalize on all those points if you want that. So those are all out there. So that's available until Wednesday night. Feel free to submit. So yeah, any questions or preferences, or should I just keep moving through and then, yeah.
Are you gonna provide a handout of the archetypes as social patterns?
So the question is, am I going to provide the kind of the systems archetypes? And I will tell you already, the second page of the exam is basically is a copy of the sheet from Kim and Lannon that has like all of the archetypes that Kim and Lannon talked about with some brief descriptions. So if you open up Kim and Lannon, there's like a sheet that has like, it has kind of like a brief overview of what the diagram looks like, and it has kind of a couple of bullet points next to it describing it. And so I will include that. So I'm not expecting you to, there's a couple of archetypes like limits to growth, balancing feedback with delay. Those are important ones that I think you should know. We talked a lot about escalation too, so I would kind of think escalation, but escalation is actually on that list. But all of the rest of those, like the tragedy of the commons, for example, I don't expect you to memorize those archetypes. I provide those for you, but I will ask you questions like, I'm going to describe a situation, and then I'll say, look back at page 2, which archetype does this best match with? Okay. Any other questions? Questions online? All right, so if we rewind all the way back to the beginning, remember we started just sort of the philosophical question of what the heck is a model? So expect to have some questions that basically, remember the learning outcomes, these are the things that I tell ASU that you are going to learn when you come out of this course. And so everyone coming out of this course should hopefully be able to define a model, should identify qualitative and quantitative models, et cetera, all of these kind of points here. And so along those lines, this idea that models answer what if questions. So coming into this class, if you're familiar with the term model, you might have associated it with math or computers or something like that. And what I'm trying to say here is models are not defined by what they are, but the questions that they answer. So that's kind of the key point that I want you to remember here, that models answer what if questions. Okay, so that's kind of the big thing there. And then, I want you to sort of think about that we have mental models that answer what if questions, but they have strengths and weaknesses. So to remember that, and due to their weaknesses is the reason why we sometimes will shift to quantitative models, which also have strengths and weaknesses. So those are some things that might want to feel kind of comfortable with. And so, of the quantitative models, there are mathematical models like the ones you might learn in 211, or Calculus 1, but they have weaknesses in that they're not quite as easy to, for one, they don't describe necessarily the whole behavior over time of a dynamical system. And the other thing is that they're not that great to look at. So they don't really communicate to stakeholders very well unless the stakeholders are also mathematicians. So that's one of the reasons why we shift to simulation models. They allow us to have a much more kind of a longer term, where we can actually see at various different time scales of the analysis. And it's a lot easier for us to communicate this by showing a graph to our stakeholders rather than one of those kind of more ugly equations that require a lot more background knowledge to understand. The downside is we don't have the analytic solutions where we can say that this variable is exactly related to this variable with this factor in front of it. We just have kind of a graphical relationship. So these are approximate solutions. They're a little more qualitative than the mathematical solutions, but it's a trade-off. All right, and about trade-offs, this spectrum is one that I'm hoping feels pretty comfortable to you. This idea that there's a model that you choose is going to have the ideal balance for your problem from realistic detail and transferable insight. It is never a good idea to just add detail to your model for detail's sake, but it's also bad to create an overly simplistic model that it seems divorced from reality. So hopefully with things like system dynamics models, we can create something that has, it's not quite a toy model like Monopoly, but it's not quite the sort of experiment that requires millions of dollars to run. It's something that has just sort of the right balance of complexity where we can test hypotheses relatively easily and get some sort of generalizable insights that then later we can then invest in making more realistic models later. So modeling is an entry point where we start in one level of model and then gradually get more and more specific as we get further and further evidence for hypotheses we test at one level. So hopefully that feels good. If any of this doesn't make any sense, or you have questions, or even if this makes you think about something that's in Unit D, feel free to interrupt me, raise your hand, leave a note in the chat. I'm just kind of walking through this trying to exorcise the demons in the room. Okay. So questions, anything. So that's our first unit, just sort of this sort of philosophical, what is a model stuff. So then we moved to unit B, and we started to actually put our models down on paper. And that's the causal loop diagrams. Big thing here, and I would read through all these and make sure you feel comfortable with them. But of course, the big thing here is, can you draw a CLD? Can you look at a CLD and understand what it's saying? Can you find the feedback loops in such a CLD? And so, and that's kind of all the sort of stuff that we talked about there. And so along those lines, we said that, well, what do we use these CLDs for? We can use them in two directions. We can say, well, we've got a mental model where we think in very coarse terms about a system. We use a CLD to help refine our reasoning to actually figure out what variables we think are involved, so that we're maybe on the way to a stock and flow diagram in unit D. Or if we're given a stock and flow diagram, we can say, well, what the heck could be going on up here that might explain the behaviors we're seeing in our simulation? Well, let's draw a causal loop diagram. Oh, I see that there's feedback loops, and these feedback loops fit into a certain systems archetype, which might be characterized down here. And that gives me more insight into what's going on there. So those are the two directions we can use these CLDs. Sometimes you do one, sometimes you do the other. So, so how do you draw these CLDs? So we have to be able to, the biggest thing is to draw links between things that depend on each other. So here we're saying that in order for, that X is causally related to C. So if C changes, it will cause a change in X. If X were to change, it doesn't cause a change in C. There's not that direction back there. And then we have to say, well, if we held everything else constant, A and B constant, if we somehow could just change C, would we get a change in the same direction or an opposite direction at X? And if it's in the same direction, we label it with a plus or an S for same. If it's in the opposite direction, we label it with a minus or O for opposite. And so it's just a way to grab the causal relationships between variables that we've identified are important in the system, or we hypothesize are important in a system. So any questions about causal link labeling? Does this start to feel a little more comfortable? Yeah.
Can we do a practice one?
In the practice one? Yeah, so I've got some practice problems at the very end, where I've got some sort of like things where I give you a mathematical expression. Like I'll say, what if X is equal to A minus B? And in that case, it would actually look exactly like this. So if X was equal to A minus B, and I guess I could maybe use my ugly PowerPoint writing. So 10, there we go, X. So if I said X is equal to A minus B divided by C, then the numerator here is exactly as currently labeled. If A were to increase, X would increase. If B were to increase, X would decrease. Now, I divide that whole quantity by C. That division kind of has a similar effect as the subtraction. So if C were to increase, it would divide X down more. So X would decrease. And so if I were to talk for this particular model, I would get rid of this question mark and I would replace it with a minus. Yeah.
Oh, so if you do that, how would you know that it's like A minus B over C and not just A minus B minus C?
Well, I would, so like on a test, I would say, if you were given this formula, how would you diagram the formula? So I would give this to you. Now, if I gave you the formula, X is, I could do that. Like I could say this is X is equal to, where they were. So alternatively, I could say X is equal to A minus B minus C, and it would be the same diagram. Minus B minus C. And so the causal relationship between these two things are identical, this is the reason why causal loop diagrams are limited in how much they can investigate the systems. So if we were to dump these into a stock and flow diagram and hit simulate, this formula is going to give us a different behavior over time than this formula. But the large scale behaviors are going to probably still be consistent with minus, plus, minus. Does that answer your question? Okay. Any other questions about this example? Questions online? Okay, great. All right, so then once we've labeled our links, we have to come up with the loops. We have to find the loops. And so you find loops by starting with a variable and finding a path, following the link arrows back to the variable. And so when we do that, as we go start from a variable like A or B or C, it doesn't matter where I start, we go all the way around and we count the number of negative links. If there are an odd number of negative links, then it's a negative feedback loop. If there's an even number of negative links, including 0, it's a positive feedback loop. So that's kind of rules are sort of down here. So here's an example of a negative feedback loop. Here's an example of a positive feedback loop. Yeah.
So in the test, I remember these by negative, positive. I don't remember them by both.
Balancing, reinforcing. Right. You should know those as well. So yeah, it's just really, it's kind of a common parlance. So I'll write this here. So this, positive is also reinforcing. This negative is a balancing or a counteracting. Now, balancing is far more common than counteracting. So I would say B and R are really the key ones to know, and minus and plus as well. So, if you're coming into balance, you're regulating, that's negative feedback. You're bringing it back to a set point, that's balance. If you're growing, you're reinforcing, that's positive feedback. Okay, any questions about this? So this will be key. Like we've spent a lot of time on causal loop diagrams this semester, so know your CLDs. Okay, and then this is just enforcing that, reinforcing, so to speak, that. So all of the different things here, vicious and virtuous cycle, know that those are both the same thing. That's kind of a good thing. Know these symbols, same here. So
I guess, let me rephrase, I know what they are when I see B or R, but in terms of labeling it myself.
Well, if you're labeling it yourself, well, yeah, so if I ask you to label a loop on the test, I might be limited in what I could ask you to do. Like I'd say, is this a plus or is this a minus? And so, so it's good to know that plus and R are synonyms for each other. It's good to know that minus, B, and C are synonyms for each other. Okay. Any other questions about this? Questions online? All right. Just going to double check here that, yep, we're recording. Always very nervous about that. Okay. All right, so I might give you exercises like this. This is an exercise we already did in class. Definitely would recommend, labeling these loops. So just for time, because I've got novel exercises at the end, I'm not going to go through it here unless someone would like to, but just as a reminder, when we work at home, or again, you can go over this if people have questions. There's a loop here, there's a loop here, there's also a loop all the way around the outside. And the loop here is going to be a negative loop. The loop here is going to be a negative loop, but the loop all the way around the outside is going to be a positive loop. Yeah. That's a good question. What about the loop in the middle? Does anybody have any comments? Yeah. The arrows don't match, right? So this looks like a loop, but that's just a trick, because if I go from B3, I get stuck. So I can't actually make it all the way around. Other questions? Great. Okay. Other things, definitely fair game for the exam is I can show you things and ask you about the error. So I might show you one of these. Since we know about stock and flow diagrams, I might show you a stock and flow diagram that's kind of annotated, kind of in a CLD type way, and also ask you for similar sorts of errors. So again, not going to go through this in great detail, but here, this basically is the wrong polarity loop. Should be a minus because there's one negative link. The one over here This one here, it looks like a loop, but when you actually try to follow it around, you can't actually get back. So this one is not actually a loop. This is an important thing I also want to emphasize. This here is still a causal loop diagram, even though there are no loops. Causal loop diagrams are used to find loops. They aren't just to diagram loops. So that's another kind of trivia sort of thing that you might imagine me asking. Is a causal loop diagram, here's a causal loop diagram without a loop, is it a causal loop diagram? And it is still a causal loop diagram because it's used to find loops. It's not just needed to diagram loops. All right, questions about this? Pretty clear? Okay. Correlation not equal to causation. This is kind of a big thing when you're drawing these causal loop diagrams. There must be a hypothetical causal relationship between the variables. If you cannot come up with a hypothetical causal relationship, if it's purely correlational in your data, then you might think, can we come up with a better relationship that actually we could come up with a causal mechanism there? So it might be that in data, we see that whenever ice cream sales go up, sunburn rate goes up, but we have no hypothetical causal relationship for why that should be the case. Now, if we think a little bit more about it, we now have a hypothesis to explain those data, and that's that as temperature goes up, ice cream sales go up, and as temperature goes up, sunburn rate goes up. So there's a common cause. So this is a better hypothesis than that one, because I can actually sort of justify this one here. So this, I should move forward with my causal relationship, not my correlational relationship. So we don't have correlational hypotheses. Correlations are just looking at the data. There is a correlation. We have causal hypotheses. CLDs capture our hypotheses about what's going on, causal hypotheses. Okay, questions about that? Pretty clear? And then the other big thing we talked about is naming these things. So, must be noun phrases. So we don't want to use verbs in these things. So costs rise, prices rise. It's hard to say when costs rise. Like, I can't do the exercise to figure out what the link label is because there's already too many verbs loaded into the word. So they have to be noun phrases. They must have a clear sense of direction, again, to allow me to label the link. I don't know what feedback is. I do know what praise is. So that's something that has to be in there. And then their normal sense of direction should be positive. So rather than saying as costs increase, so do losses, it's better to say as costs increase, profits decrease. So if I have a choice between these two, I like to make the variables always positive and any negative relationships show up in the links. And that's just a convention that if we all agree on that convention, then all of our causal loop diagrams tend to agree as we draw them as well. So this is technically not necessary. All the math works out fine if you don't abide by this. But if you do abide by this, it's much easier to communicate with other modelers because all modelers are going to expect you to do it this way. Yeah.
I don't understand why the feedback from Boston
So the question is, why is this one a bad one here? Because it seems like the arrow is communicating the directions of these things. Well, it's kind of like you've loaded up more semantic meaning into the arrow than we want in a causal loop diagram. So the arrow is really just meant to be, if you get a differential change here, what differential change will you get here? And if I forget the arrow and say, if I get an increase in feedback, well, an increase in feedback could be positive feedback or it could be negative feedback. So I don't know what type of feedback. And that's going to affect my mental attitude depending on whether it's positive or feedback. And then also my mental attitude, it's not clear to me, like you can have a good mental attitude and a bad mental attitude. So attitude seems like it has multiple dimensions, whereas morale really seems like there's only one dimension. Praise really only seems like there's one dimension. Any other questions about that in class or online? Great, okay. So this is the same sort of things. Moorcroft tells us that words should imply measurability, which is a nice little tip. So this is just sort of restating the stuff from the previous slide. So from there, we should be able to start drawing these causal loop diagrams. So if I give you a simple system like this one, we understand how the system works. So I show you this picture, you know that someone looks at the water level, and based on the water level, they adjust with their hand the flow of water. Because we know how this works in our minds, our mental model, we should be able to diagram that out in a causal loop diagram. And so you should be able to go through here and be able to sort of identify variables like this water level. Well, that probably goes onto one of these spots, the flow of water, that maybe goes onto one of these spots. And then based on those things, we know that as you increase the flow of water, that will increase the water level. So that's a plus. And as you increase the water level, then the person will reduce the flow of water. So that's a minus. And so this is a balancing loop or a negative feedback loop. And we can think of it as being a balancing loop because we can think of it whenever the water is under the level, the system's out of balance and it's coming back into balance. So any questions about this? Going from a simple description of a system into a diagram summarizing all the causal relationships. Questions online? All right, going through this just quick so that we have plenty of time here. Not going to go through every exercise. We've seen this exercise again. Like I mentioned when I first presented this diagram, this is not a good diagram because births is mentioned twice. But still, I would invite you to go through and say what happens when births increases the population and vice versa. What happens to population and food supply? As population increases, what happens to food supply? As food supply decreases, what might happen to death, and so on, and see if you can get all that working. And then we did this example, this sort of kidney-shaped example here in one of the assignments. I forget which assignment that was now, in the B's, B1 maybe, where we end up getting two positive feedback loops, but this positive feedback loop has got all positive links. This positive feedback loop's got two negative links. And so this fraction of VCR sales to VHS sales causes them to compete. And so this is one of these success to the successful systems archetypes. But hopefully you can, if I were to give you an unlabeled causal loop diagram like this one, it would be something that's a little more contemporary. So you don't have to think about like what the heck's a VHS tape and all those sorts of things. But hopefully you still could walk from variable to variable to variable and label these links. Yeah.
For the midterm, are we supposed to do anything on Vensim?
Questions, is there any Vensim on the midterm? The midterm is not meant to be a practical exam. So I'm not going to ask you to do any modeling with Vensim. It's all Canvas-based, it's all automatically based. Do expect, though, that I could show you diagrams and ask you questions about them. DT is fair game because we talked a lot about setting DT. So I won't ask you to build a model and run it or anything like that, but I will expect you to be able to be model literate. So be able to look at a model and answer questions about it. Okay, great question. Thank you for that. Questions online? All right, let me make sure there's no anonymous questions coming in since I put up this page. All right, looks good. All right, so then we're into Unit C, where we start talking about all the system archetypes. Again, I provide you a table of all the system archetypes from Kim and Lannon. So you don't have to put that on your cheat sheet unless you want to emphasize something special. Like you're like, I really had trouble differentiating between these two archetypes. I'm going to put out some extra notes. That would be a great thing to put on your cheat sheet or crib sheet or whatever we're calling it, your note sheets. But I will give you kind of an overview of all the archetypes that Kim and Lannon talk about. And so the big things here, be familiar with this kind of event-oriented worldview as kind of our feedback systems approach as being a rejection of this idea to sort of a more complete view of the system, where we include the actions and their side effects in our model and hopefully make better decisions about our actions that maybe have side effects that are less negative in the long run. Kind of the point here of this. And with that in mind, we are trying to flavor this, or trying to get a flavor for various system archetypes and their behaviors over time. So a balancing feedback loop with delay, even without the Kim and Lannon, this is such a simple and basic fundamental component. You all should know that a balancing feedback loop with delay tends to produce, can produce oscillations, can produce very slow balancing action and very fast balancing action. So based on parameters, quantitative parameters, how long these delays are, you can get these different actions. But so oscillations are often caused by balancing feedback loops with long delays. Supply chain problems we have now are often attributed to balancing feedback loops with delays, for example, boom and bust that you see. So that's all I'm kind of saying here. Oscillations, balancing feedback loops with delay. Another kind of common one, this limits to growth or S-shaped growth, a reinforcing loop next to a balancing loop. No growth goes on forever. There's always an eventual reinforcing loop, even with climate change. There are reinforcing, well, of course, there's reinforcing parts to climate change, but there are balancing parts to climate change as well that will cause climate change to round off in the long run. But when we think about the time scales of these things, we may not be able to count on those natural things. And so that's why if we include the whole system, we can then better defend whether we really need to worry about climate change or not. And if we find out that the balancing that we know is going to eventually be there is way far out, then maybe we need to be a more aggressive balancers today. So that's a big reason why we have to consider both of those. So S-shaped growth, reinforcing, followed by balancing. The growth with overshoot just combines the two of them together. And so in this case, we have reinforcing followed by balancing, but then in the balancing loop, we put a delay. And when you get that, then you tend to get this sort of almost S-shaped growth, but then these oscillations. And that, this basic pattern here is kind of this limits to global growth model from Forrester. The difference between whether the world collapses or the world kind of steadies out here has a lot to do with this delay right here. And so, so that's an example. We put those two things together, then you get combinations of the two of them. So it's good to sort of know that archetype. So I'm not trying to get too complicated. Those are the three that I would say you should sort of know. That Kim and Lannon's archetypes are even more complex. And I've given you those, but these are just like fundamentals, like basic Lego building blocks of system dynamics models. Okay, questions about any of those three? Okay, and then in Kim and Lannon, the 4 ways we can use the system's archetypes. I'm not going to ask too much trivia about these. Like, I'm not going to ask you to define what it means to be a lens, but I could use language that refers to these different things. So, so you need to sort of be familiar with, if I was going to say, using this system's archetype as a lens, what would be, this component in the generic, this component of my specific narrative in the generic archetype, so kind of know what I mean by using it as a lens. So kind of be familiar with these general ideas, but again, these are not things that are like these solid definitions that dynamic systems modelers out there are going to expect you to know. But if I were to use them in context, I would expect you to kind of know what I meant between about a structural pattern template or a dynamic theory. So like with lenses, I give you a system, know that we have different ways different archetypes that we can put on this system to give us insights into it. With structural pattern templates, that helps us simplify systems from ugly webs like this to something that is more coarse-grained, maybe makes more high-level sense. Know that dynamic theories help us provide a dynamic explanation for behavior over time that we're already seeing in systems. And that kind of on the flip side of that, then tools for predicting behavior, then these, if we take this endogenous perspective, and that's a term you definitely should know, then that's telling us that that if we really chart out, if we look at these systems dynamics, then we know that every reinforcing loop is always going to have a balancing loop somewhere at some time scale later. And so that tells us that we can predict that even though we're seeing growth now, we'll eventually see it round off. And so the tools for predicting behavior helps us predict scenarios that could happen in the future, even though we haven't seen hints of them in the present. Yeah. Yeah, okay, sorry, yeah, great. So endogenous perspective here. Does anybody have a definition they would like to share of when I say we take the endogenous perspective in this class? Any thoughts? So there's endogenous versus exogenous. So definitely exogenous sounds like from outside, endogenous from inside. So what does that mean? Yeah, there's a stretch or a hand. I think a stretch. Do you want to give it a shot?
Yeah. Is it when you you're doing a model?
It's so the same was that when you're modeling and you're not taking into account any outside factors, that's effectively it. And so I guess I would strengthen that a little bit and say it's when we assume that all behaviors of interest can be explained deterministically by looking inside the system. This can be contrast to say, well, why did this terrible thing happen? Oh, we couldn't have expected it. There was an asteroid that hit the Earth or something like that. So, you know, there can be endogenous extinction events. We can drive ourselves to be extinct. There can be exogenous extinction events. So we might model how we go along every day, but our model doesn't include the effect of an asteroid, and suddenly an asteroid hits the Earth and we're dead. So that wasn't in our model. And so if we want to account for those types of extinction events, that would take like the exogenous perspective. What's the probability of this external shock hitting the system? Endogenous is deterministic, non-random. What can we predict based on our everyday behaviors and causal relationships inside the system?
So endogenous perspective, deterministic inside the model?
I'd say deterministic, non-random inside the model. In contrast with random, non-deterministic from outside. Okay. So any other questions about these sort of systems thinking things? All right, and then the Unit D stuff, most recent stuff about stock and flow models. So, so in Unit D, you know, again, there's no practical part, so I'm not going to force you to build a Venn model from scratch and run it and make sure that it passes some unit tests or something like that. But again, I might show you some of these models. And so, you know, so sort of generally understand how these models work. They're kind of based on this kind of compound interest formulation where you start with some initial stock level. You figure out how much will be added to that stock. You end up adding it to the next you know, the next stock level, the next time instant, and then you repeat. That's what's going on behind the scenes when you're doing these computational models. And that allows us to simulate, you know, of course, a bank account, all these steps through here, which we can go through, or analogous to that, growth of bacteria. And so we were able to build these, you know, these models here where we could start out with a parameter like the average time between reproduction events, an initial stock number of bacteria, the flow of new bacteria, which is just the number of bacteria times the per bacteria contribution to new bacteria. So that stock and flow right there, those two things are kind of really important. And then we know that the behind the scenes, VinSim or Insight Maker is just taking the previous number of bacteria. They're taking the flow from the previous one, multiplying it by dt and adding it. So nowhere in any formulas you write should dt show up, because in a VinSim or whatever, then it's doing that for you. When we manually have to code it in Excel, we had to manually put this dt. But if I ask you for a formula, I'm not going to ask you for, you know, specifically something Excel specific. If I ask you for a formula that relates to a stock and flow diagram, nowhere should dt show up. But I might ask you, you know, what's a good value for dt based on, you know, graphs that I show you. So I think I've got maybe one of those coming up here in a second. So, so yeah, so understand kind of how this table works, but I don't care that much that you're going to come away with this class with the ability to do numerical simulations in Excel, because this class is supposed to enable you with tools like Vinsim and Insight Maker that make it much easier to do that. But I want you to at least at one point have exposure to what's going on behind the scenes, so you can look at these tables and understand the tables, even if you don't quite remember the formulas that are driving the tables. Yeah, so that's kind of all I'm saying here. And then generally the definitions here. Stocks and flows. The stocks kind of capture the history of the system. They can't change unless there's flows. So at no time in your diagrams should you ever see, and this came up, there should never be causal links that terminate on flows, or sorry, on stocks. So because you don't update any formulas inside here, you only update initial conditions. If you want to make a stock change, the variables need to be connected to the flows of the stock, because the flows of the stock are what control the changes of the stock. Yeah.
So inside that would look like improvement minus turnover.
Yeah, but Vinsim or Insight Maker will do that for you. So yeah, this stock is implementing the integral of recruitment minus turnover. So, but when you draw the flows in a tool like Vinsim or Insight Maker, it will update that for you. The only thing you update in the stock is the initial condition. So that's all that we're saying here. Inside the stock is an initial condition. This down here, recruitment minus turnover, that's done inside Vinsim. You don't actually have to update this. You have to know what's going on, but Vinsim or Insight Maker manages this for you. And so the formulas you do have to put together come from these causal links. So we already kind of gave some examples of this, where if I have a formula which is centered on a variable, I can only use variables that are coming into that formula. So this formula can use B and C because B and C are connected to it. So any questions on the causal, on the coordinating networks, the informational and causal links, and how they contribute to the formulas you're allowed to use inside here? Questions online? All right. We talked a little bit about sector maps. So I might ask you about the term sectors and sector maps, just because it is a useful term. As you get really big and kind of ugly diagrams, then sometimes it's nice to break them up into sectors. But notice that the sectors themselves, as far as the computer is concerned, they don't care about which sector is which. That's just a useful way for you to break up a model to make it easier for you to program the model, and also easy for you to present the model to stakeholders. So for example, we can break up a complicated model into 4 separate sectors, where each sector looks like a simple model, but because they share variables, like drug seizures shows up here, drug seizures also shows up down here. So this is actually a much more complicated web, but we've been able to break it up into 4 small sectors. So this is what Moorcroft calls the sector map. It's a rough, but these arrows don't really have a lot of meaning. This is just sort of saying most of the causality flows from here to there. But in reality, there could be other connections that aren't pictured here. This is just sort of a high-level view to make it easier for a stakeholder to understand your model. Yeah. Okay, so the question was, are converters and CLDs? Converters are a more quantitative thing. So I would say that in CLDs, we just have variables and links. We don't get to the distinction of converters until we get into stock and flow diagrams. So I would say in stock and flow diagrams, we have stocks, we have flows, and we have auxiliary variables or converters. And so why do we call it a converter? It's because it's taking it from one unit, like drug supply gap, and turning it into another totally different quantity, pressure for price change. So this path, like, it looks like I could have gone directly from drug supply gap to change in street price. And I probably could have come up with a formula to do that, but I've broken it up into 2 steps so that I can communicate that there is some way, like some data out there that would suggest that I could go out and look at real data for drug supply gaps and how it affected the pressure for price change, and that would effectively kind of convert from this gap, which would be like in kilos of whatever the drug is, to pressure for price change would be in a totally different unit. So that idea of converting units is where this kind of converter comes into play. So we don't call them converters until we're actually using formulas. And so but these things might all show up on a causal loop diagram, but I would just call them variables of them. All right, any questions about this breakdown of the components of socket flow diagrams? My question slide again. All right, so with that, I've got a couple of practice problems, just some sort of examples, some things to think about, and their solutions. So these are novel. So here's an example that this is probably more work than I would have you do on a midterm problem, but it's great and a great exercise. And so this is an example of the causal loop diagram that describes what happens when you get a cut and it gradually starts clotting and then turning into a scab and sealing up. And so I wouldn't give you something that's so, like most of these, I think you could probably figure out what's going on, even though if you've never heard of thrombin, you could probably figure it out based on the kind of context here. But an example I give you on a midterm, then I wouldn't, it would be a little bit more direct or be a little bit more familiar to you. Maybe it'd be ASU specific or something like that. But we could walk around all of this sort of thing and label all of these links. And so, you know, we could go through here and say, well, if I get more thrombin, without even telling you what thrombin is, I think it's a pretty good guess to say that with more of this thrombin, I'm going to get more formation of these fibrin fibers. And so, you know, you can go through and we can gradually turn all of these question marks into pluses and minuses. And after we do all of that, then we're going to see that there are a number of loops that we'd have to label, like this one here. And we could go through and find, I think there's a couple other loops as well. And then we could try to see, are there any system archetypes that kind of look like might be applying here? Me as a systems modeler, I would expect that there's probably an S-shaped growth archetype built in here without me even you know, knowing everything about that. Why would I expect that? Why would you, so if I'm talking about blood clotting, why might I expect that this causal loop diagram would end up looking like S-shaped growth? Any thoughts? Yeah.
I would imagine you have to think about a wound, like when you open up a wound, it bleeds, and so it stops bleeding and starts to heal. So that would look like that.
Right. So the comment was, if you think about it, whenever you get a wound or a cut, you get a lot of activity initially to stop the bleeding, but then gradually over time, technically your innate immune system seals that thing up, and then eventually you know, you go back to normal. So we would expect that there's going to be a growth loop that, and so if I think about here, amount of thrombin increases fibrin fibers, which will, with more fibrin fibers, that is going to maybe increase the size of the clot. And with an increase the size of the clot, then you might expect that maybe this amount of thrombin might maybe decrease. And so maybe I would end up getting a balancing loop here, but then a reinforcing loop around the other side. So the idea here is that if we walk through this, and I don't think I'm going to go through this whole example, but we would expect to see an initial growth loop, which would be your body mobilizing to fill in that new gap. And then gradually, as you get a clot forming, then it settling itself down and going back to normal. So we would expect to see an S-shaped growth. So that would be kind of an exercise you could do. And so I've done that all the way through here. And apparently I got my own terms wrong here. So this here was actually the reinforcing loop. And so that's the reinforcing here. And then if I were to go down back through here, I'd see there are other balancing loops. And so if I look through here, I see this loop up here, that's a balancing loop. Let me make sure I draw this in the right direction. I think it's, well, so that's the wrong direction I drew that in. Oh, no, maybe it's the right direction. So that's an example where this is the initial formation of the clot. And then up here, we see that as the size of the clot increases, the wound opening decreases, which actually decreases the fibers. And so this is the balancing loop that cuts off the action as things seal up. This is the reinforcing loop that recruits the clotting agents to bring things together. And we might be able to find other loops here as well. So that's kind of, again, a more complicated example. And then we hopefully then note any interesting archetypes. Again, we're kind of expecting an S-shaped loop archetype. And so I think I've got on my next slide, there's the full solution there. So any questions about this? Okay. All right, so if I show you different simulation outputs, could you guess the right value of dt? So here's a couple here. I've got dt equal to 0.1, 0.05, 0.01, 0.005, 001, 0005. So they're getting smaller as I go from the top left down to the bottom right. And so a key thing to look at here is the axis scaling. And they all have the same scale here. So that's something that can trip you up, as if there's different axis scaling here. So then the next thing I look at is, make sure they're all going for the same time, the same time length, and they're all going for 6 time units. So from there, I can look at the graphs and compare them. Now, can anybody have a guess as to what might be the optimal value of dt? Yeah.
Bottom left, 0.005.
0.005. Why would you say the bottom left?
Oh, it doesn't seem to change with the next 2 values.
Okay, so I think that's a great answer. So if we look here, we say that the graphs really look pretty much the same for all smaller values of dt. Now I might want to look up here and say, does this graph here look much different than this graph here? And these two, and they're not next to each other, this one isn't that different from that one. There is a slight difference here. So it's a little bit of a judgment call as to whether it should be this one or this one. And if I were to ask you to make such a call, I would make it far more clear. Like on a midterm, I'd probably give you like this one, and this one. And I hope you can see it if I gave you the top left, the bottom left, and the bottom right, then it's probably best to choose this one here. Because as I showed you with Vinsim, if I crank the dt down really small and hit play, Vinsim just runs and runs and runs. Yeah.
So the goal is basically get as small as you can get without it. Yeah.
That's right. So the goal, to restate that, the goal is to get it as small as possible without the behaviors over time looking identical if you go any smaller. Because you always can go smaller, but if you go smaller and smaller and smaller, the downside of all of that is your simulation will run forever to generate one behavior over time. So this balance here, this allows me to have a fast simulation that's also accurate. Okay, and so that's all I'm kind of summarizing here. No significant changes in plot after this, so that's the one I would pick as well. Okay, any questions about that, picking dt? So dt doesn't go in any of your formulas, but if I were to ask you about dt, these are the types of questions I'd ask you about dt. So don't be tricked by any formulas that have dt in them. Don't put dt into any formulas you implement or in any sorts of responses to questions, but this is what you should know about dt. Okay, what else we got here? So this here is, I'm just pointing out here, be careful about the axes because Vinsim, as you plot it, it's going to choose an axis scaling automatically unless you manually go in and change it. I haven't showed you how to do that. So when you're looking at these graphs, I tried, this would be a kind of a cheap trick if I threw this out there. So I'm not going to try to trick you this way, but I make mistakes sometimes. So it's always good to double check. But if I give you plots and you're comparing them, make sure that the axis scaling is the same. Or you've adjusted for axis scaling when you're thinking it through. Other things. So I like this example. I borrowed this example from another text. So the question here is at what time is the hive the fullest? So that's a simple stock and flow diagram over here. So we've got bees in the hive. So imagine we're sitting here and we're watching bees come in a hive at a certain rate and go out of a hive. And if we have some data here, the solid line are the bees entering the hive over time, over this 30-minute period. The dotted and dashed line are the bees exiting a hive over that same period here. Now, if you look at these lines here, so think of the dark or the solid line as inflow and the dot dash line is outflow. If I look at this period here, can anybody give me a guess as to when when it's the fullest? Do you have a guess? Why do you say 15? Okay, so the suggestion here is maybe it's 15 because that's when they cross. So why do you think them crossing is an important event? Okay, so at that time there's no bees. There's no bees leaving at that point. There's kind of, well, there are bees leaving, but they're perfectly balanced by the bees coming in. Was that what you were about to say? Right. Any other comments about why 15 might be the right answer? So when we think about it, let's think about the net flow. Before 15, the net flow is positive. So I'll say net is positive. And so that means that the inflow is always greater than the outflow. But after 15, the net is negative. So that tells me that before 15, the population is rising. After 15, the population is falling. Or if you go back and think about your derivatives, or calculus, if you were trying to maximize a function, you might take its derivative and then see where it is equal to 0. Well, when these two lines cross, that's when the derivative of the bees in the hive is equal to 0, because that's when the inflow is equal to the outflow. So all of those things together tell me that the peak residency is right there at 15. So this is when entering is greater than leaving is greater than entering. So I think it's a really cute question. So being able to think about that, and there I've got the little drawing here of the derivative there. So being able to reason through that question, if you can do that, you're in really good shape. So any questions about this? Only got a minute or two left here. Let's see what else. Other thing, formulas. Definitely sort of try to get an idea on how to process these formulas and maybe form them. I don't have enough time to go through this one in detail, but again, there's a video online. I will go to kind of the answers here. I wouldn't ask you to guess all of these formulas, but I might give you a stock and flow diagram, and then based on units, for example, or some other information, I might say, can you pick a likely formula for this one down here? So I might say, I might give you the causal link polarities, for example, and based on the polarities and the units, can you pick the most likely formula that would be used here? That'd be kind of an example. And we could kind of reason through this simple population model here for why the formulas should be this way based on the rates we expect and so on and so forth. So I talked through that in the kind of the video example. And then the only other examples I've got here are these more arithmetic ones. I give you a formula, I ask you to draw or pick the causal loop diagram. So for this one, the causal loop diagram you'd expect looks like this. I kind of already did an example like this earlier. For a more complicated one like this, we can combine all of those things together and we can get this sort of CLD. And so again, I'm almost out of time, so I don't want to go through this in detail. And then the other sort of thing is I can make them a little more sophisticated and get a little bit more into calculus here. And all you really have to remember is that anything that shows up with a derivative is a stock. So I know the A, B, and C, those are stocks. And the dA dt, those are the flows. And so I already know that an inflow is positively related to the stock that it's tied to. And this is telling me that variable B is positively related to the inflow for A, variable C is positively related to the inflow of A. Here, I could either say variable C is negatively related to the inflow of B, or I could say that variable C is positively related to the outflow of B. So there's different ways I could break these things up. So I can turn these things basically into stock and flow diagrams like this one. And then I can then ask, questions about those. So try to be able to take a simple expression like this and turn it into a stock and flow diagram, or maybe be able to reason the other way around that. So there's alternative ways. Here's the ways I can label those links. And remember that there are, for example, implicit negative links coming on outflows. So there's a negative link from outflow back to that one there. And I think that's kind of, label these loops here. And then that's basically, so if I draw the stock and flow diagram, I can turn it into a CLD. I could ask questions about that. Again, I go in more detail about that on the video that's posted online. All right, that's 416. So that's all I've got for you. I'm just going to put these reminders up here again. And everybody gets attendance for free today. So if you have any other questions, I'll be here after class for at least a few minutes. Otherwise, feel free to send me an email. Good luck on Thursday. Thursday, Friday, and Saturday's availability window. It'll open up on Thursday. And if there's any questions online, I can also take those. All right, in that case, I am going to end the meeting and see everybody on Thursday, or not.